இதுல போட்டிருக்கு, எதுல நிக்கிருக்கு இப்போ? சரி, சரி. கொஞ்சம் லோகோ பார்த்து இது வேணாம், அப்புறமா பார்க்குறேன். நல்லா இருந்தா அப்படியே எடுத்துக்கிறேன். ப்ரொஃபஷனலா இருக்கா? ஏன் இப்படி சொல்ற? இது நல்லா இருக்கல, இது மட்டும் கீழே உள்ளது மட்டுமே எடுத்துக்கலாம். அதுதான் நல்லா இருக்கு. நல்லா தான் இருக்கு, சூப்பரா இருக்கு. ஆனா அது இப்போ ஒரு பிளாக்ல பிரிண்ட் ஆகணும்னா எப்படி இருக்குன்னு யோசிச்சுப்பாரு. இது மட்டும் பண்ணலாம். ஐ ஸ்மால் ஐயா இருக்கணும்னு சொன்னேன்ல. கேன்வா ஃபைல் தானே. சூப்பரா இருக்காது. இந்த பிளாக் நல்லா இருக்கு, இது மட்டுமே எடுத்துக்கலாம். ஆனா இல்ல வேஸ்ட்னே வரலையே. இல்ல சூப்பர், தேங்க்யூ. இன்னைக்கு வர முடியாது. ஓகே, நான் ஸ்டார்ட் பண்றேன். பாய். Okay, good evening everyone. So we'll start the session. Um, Hope you all already know me. Those who joined new today, I'll just give a small introduction about me. So I'm Saravanan, PhD scholar and Prime Minister Research Fellow at Department of Civil Engineering in National Institute of Technology, Tiruchirappalli. And I have my bachelor's in civil engineering and my master's in environmental engineering. And I am now working in the field of solid waste management, and my research area is in landfill mining. And I become the Prime Minister Research Fellow in 2021, and from now 2021 onwards, I'm taking NPTEL TA-ship as a part of PMRF TA-ship program. So this semester I'm taking air pollution and control, and this is the fourth week of the problem solving session of NPTEL course air pollution and control. So, hope you all enjoying the course. And in the first week, we have discussed about the air pollution definitions and what are the air pollutants and what are its impact to the environment, human health, and other species like birds, animals, as also to the materials, what are the impacts we had seen. And later, we have discussed about global and Indian scenarios of air pollution. And then we have discussed the what are the episodes that happened, and then accidents, and then impacts to the climate and to the atmosphere, like both by whole biosphere, how it affected that and all we have discussed. Then we have discussed about in the last week, we have discussed the standards given by different countries for the air pollutants, and then how to measure the air pollutant in different methods that and all we have discussed, and the one modeling technique, that is Gaussian plume model. That's what we are going to discuss in brief in this week. So without knowing the concentration of any pollutant, we can't arrive to a conclusion whether the quality of the air is higher or low. That's what we have discussed in the last week, AQI standard, air quality index. So that will give you any common public also can understand what is the air quality with a color code or with a single number. With the representative of all the air pollutants concentration, we have converted into a sub-index, and that sub-index was converted into a AQI value, a single value, by incorporating the concentration of all the parameters. That's what we have discussed, right? So this week we are going to discuss how to model the concentration of pollutant at different points. When you are operating an industry or you are an environmental consultant, to measure the concentration of pollutant which is emitted from an industry chimney at 2000 meter, that is 200 km away from the industry, at a location in the ground level or at the height how much pollution concentration it will be there. That and all, if you want to measure, how to model or how to measure. That's what we can do with the Gaussian plume model. Okay, GPM. That's what we are going to discuss today. So during the lecture, if you have any doubt, please post it in the chat box, or you can unmute and you can ask. Okay. So the first 1 hour, I will just move on with the lecture presentation. What professor has taught in his videos, and the next 1 hour, we are going to discuss about the older assignments problems. Okay. I hope you are done with the first three assignments, and you can check the marks in the SYM portal. And tomorrow is the deadline for the fourth week assignment. Okay. So we'll start the session. So this week we are going to discuss about the Gaussian dispersion model for the point source. So we have lots of sources like based on source we have differentiated the air pollution into point source, area source, line source. So all the model we are going to discuss today. Okay. So how the pollutant concentration can be measured at different points when it is emitted from a chimney or from an industry as a point source. That's what we are going to discuss in this week. Okay. So as I mentioned, if there is any chimney, if this is a chimney, assume to a height of around HS, that is the height of the chimney, and then the plume that is coming out. Plume is the pocket of air or the air pollutant that is coming out of the chimney due to buoyancy that will rise to a point that is called plume rise. The total height of chimney plus the plume rises will be your effective height, that is capital H. Please understand the notations. Small h will be your chimney height, del h will be your plume rise, and the total height will be your effective height of the stack. Okay. Then from there it will be emitting and it is flowing in a direction of the wind because wind is coming in this direction as mentioned here. So it's flowing in a direction, so it will follow a conical pattern. So if you see here, it will dispose in y-axis as well as the z-axis. Y is transverse, z is vertical. So the line is x-axis, that is the wind direction, and it will extend in both y direction as well as the z direction. So if you want to measure a concentration at the ground level, then both y and z will be zero. Only the x distance will be there. So if you want to measure away from the center line, then there will be a x, there will be y, and z will not be there. If you want to measure above the center line and somewhat away from the center line, then all the three parameters will be there, x, y, z. So this is what the coordinates. So if you are asking to measure the ground level concentration at 2000 meter away from the industry, then only x will be 2000 you have to keep. So this is the concept. So if you want to measure 50 meter away from the center line, where the concentration will be more, at the center line or at the point away from the center line? It will be always more at the center line, and it will reduce when it is away from the center line. That's what the normal distribution. So at the center it will be higher, and both the sides it will be lower. If you are seeing the same in the z-axis, it will be in the normal. So at the center it will be higher. If you move towards top and bottom, it will be lower. That's what the conical pattern of concentration. So if you have attended the GATE exam, ES paper, that is environmental science and engineering paper, last Saturday I have given the GATE exam 2020-25. So in that, 4-5 questions were asked from air pollution and 2 questions are from Gaussian plume model. So they have asked about the assumptions and this x equal to 0 problem. So this is very important in air pollution. So kindly concentrate on this. It will be important topic. Okay, so x-axis will always be in the wind direction, y-axis will be transverse to the wind direction, that is a cross wind direction, and z-axis will be your vertically upward and downward directions. Okay, so plume, as you know, this is the one air parcel emitting from the industry. So based on different buoyancy condition, it may rise more, it may rise less. Also based on the temperature, exit velocity, everything will determine. Also the wind direction will also determine. That's what we are discussing here. The parameters affecting the concentration of air pollutant. First is the wind direction. So initial direction of the transport of pollutant determines the wind directions. Okay, so where it's turning, that is your wind direction, and it is inversely proportional to increase in the wind angle directions. Okay, so wind speed. So if there is a huge wind speed, that is a higher wind speed, will give you more dispersion. If it is a slow wind, then you will not get any dispersion. The pollutant may get concentrated. Okay, increase wind, and also if you see the wind speed will increase with the height. If you have studied fluids, then you know the wind speed at bottom. If you measure and if you go with the height, the velocity will be more. You like that it will move because Air is also a fluid, so it will flow in that direction only, in the same pattern. So wind speed generally increases with the height, and buoyance versus plume rise is affected by the wind speed. Okay, so if you see, if the wind is 6 meter per second, then the pollution dispersion is more. If it is only 2 meter per second, then the pollution dispersion is less. And the turbulence is the one which will be caused due to some obstacles like irregular motion, some buildings, some trees, or any clouds. If it comes in the wind direction, then the wind will form some eddies. That is a circular motion. That is the turbulence of the wind. Turbulence is another factor which affects the wind direction. That is highly irregular in motion. Okay, so for the Gaussian plume model, we need the wind direction, wind speed, and the turbulence that is caused by the wind. So these three factors need to be considered. Okay, then wind speed you can measure, wind direction you can measure, and the turbulence, based on the turbulence you can give the stability class like A, B, C, D, E stability class we have discussed in the last week. Okay, so to derive the Gaussian plume model, what are the assumption we can take? The plume should spread in the molecular spread due to molecular diffusion. That is the main transport mechanism. The molecular diffusion is the main transport mechanism by which the plume is spreading or dispersing. And then the time required for the pollutant to travel to the receptor is neglected. That's why it's called steady state. Because steady in the sense the concentration of the pollutant with respect to time will be zero. So it is not changing with the time. That is called a steady state concentration. Then always it will follow normal distribution. That is what very important question. So as I mentioned, any direction if you take, it will be of normal distribution. Normal distribution you have studied in mathematics. It is like a bell-shaped curve. So at the center it will be maximum. At both sides it will be skewed. It will. So if you see it is 10 milligram per meter cube. Here it will be 5, here it will be 2, here it will be 1. So like that it will reduce in both the direction. That is called a normal distribution. And you have to assume in the x direction there is no diffusion. Only in y and z direction there is a diffusion of normal distribution, you can see. And uniform continuous emission rate. That's why there is a steady state. Every time the chimney is assumed to emit something. And then wind speed is constant. You can't vary the wind speed every time. That is the assumption in Gaussian plume model. But actually it will not happen, but these are all assumptions. And if the terrain is flat, that is very important. The terrain, you have to assume the flat ground. You should not assume any mountain is there on the wind direction at all. It's not there. So we are assuming the plane is terrain is very okay. Then the pollutant dispersion follows normal statistic distribution. Shape of the plume is conical, and then there is no deposition on the reaction of the surface. So whatever you are emitting, that is only disposing, not reacting. That is one of the assumptions. So if you emit 100 microgram of ozone, then you have to get the same 100 microgram in if you add all the pollutants. So you have to assume there is no reaction. Okay, so as I mentioned, this is the wind direction. So this is the transverse direction of Z, and this is the transverse direction of Y. So it's following the normal distribution pattern. And you have to understand the symbols. As I mentioned, concentration is C. That will be in your gram per meter cube or microgram per meter cube, because in 1 meter cube of air, how much your pollutant is there? Anything, PM or ozone or any pollutant, you can say volatile organic compound or NO2, CO2, SO2, any concentration is C. It should be mentioned in the unit of gram per meter cube. Um, okay, so somebody is trying to share their screen mistakenly. Okay, well, and emission rate is Q, that is Q per centimeter second, that is gram per second, that is from the chimney. From the chimney per second, 10 milligram of CO2 is emitted, or 100 milligram of CO2 is emitted, that is emission rate. Wind speed is, as I mentioned, U, and then the standard deviation, horizontal direction of the plume is sigma Y, because as I mentioned, it's a normal distribution. So at the horizontal direction, it will be sigma Y. In the vertical direction, it will be sigma Z. So this is the two coefficient we have to mention. Its unit is in meters. Then the physical stack height is H. Effective stack height is capital H. That is addition of H plus that plume rise. That is del H. That will give you your effective stack height. Okay. Then downwind direction is X. Along the wind direction it will be X. Crosswind direction is Y, and the vertical direction is Z. That is the receptor height above the ground. So if I want to measure, there is a chimney and I want to measure, I am standing here at 1 kilometer and my height is 1 meter. So Z will be 1 meter, X will be 1 kilometer, and then I am 10 meter away from the center line. Then Y will be 10. So okay, you got it how to measure the coordinates. Then Gaussian-Blum model derivation will assume um, the transpose of mass within a small control volume. So you assume here the pollutant is emitted and here the receptor is there. So it is spreading in a conical pattern. I am taking only small cube for modeling the concentration, and then I am integrating all the cubes to get the total concentration. You got it? So every derivation will follow will formulate from a small cube or small piece of it's a control volume, we can say. Then the transport of mass in this x direction will be depends on the average horizontal wind, and then the y and z direction depends on the turbulent motion. Because from here, how it will reach in the x direction based on the wind direction and wind speed, and why it's reaching in z and y direction because of turbulence in motion. That's why it's spreading in both y and z direction. It's moving in the x direction due to horizontal wind. That are the two transport factors. Then change in the x direction you can calculate based on the mass balance. Whatever emitted here will come out here also. So the net change in the mass flow will be mass in minus mass out will be your net change in the mass. That can be calculated based on Cu, A, Y, Z, because if you cross out all the unit, you will get microgram per second. That's your mass flow rate. Rate is per second. Mass is microgram. So mass flow rate is microgram per second is your mass flow rate. So you can get this by multiplying all the C, U and A. The U is wind speed, C is concentration, A is area in the Y Z direction. So it is in, out you can directly take by this, and then if you subtract this two, you will get the net change in the mass. So if you derive by same for Z direction and Y direction, and then you can sum up all this overall expression, you will get like this. It is for small mass as I mentioned. So to get this is a what equation? Differential equation. So as we studied in mathematics, any differential equation can be derived by what we say like OD ordinary differential equation can be converted into a general equation with the characteristic equation and a particular integral. Like that, if you assume with the boundary condition of del C by del T equal to 0, because we know assumption is steady state. So concentration will not change with the time. So del C by del T will be your 0. So if you fix this into the equation, you will get the final equation like this. And then you have to convert this into general equation, general solution for the second order partial differential equation. You will get this equation. Then that you have to integrate to get the k value. That k value, if you substitute back, you will get this equation. This is your final equation, and you have to define the parameters sigma y, sigma z, and because whatever the dy, dx and all confusing, so whatever the small parameters that and all I am merging and finding sigma y and sigma z as a coefficient. So the final equation will be, this is a general equation to calculate the steady state concentration of air contaminants. So this is the final equation of Gaussian-Blum model. Whenever you want a concentration at any XYZ point, you have to take the emission rate, the flow rate, and the wind direction, sigma y, sigma z based on x, and why there is no x in this equation? Because x can be used to calculate sigma y and sigma z from the tables and the graphs, okay? And then you know the y, you know the h, effective stack height, and z, sigma y, sigma z, you can just substitute and you can get the concentration of pollutant at any point away from the source in the wind direction. Okay. So if you want to get the ground level concentration, then substitute z equal to 0, but y is there. Then the equation will become like this, because 1 by 2 will be your 0.5. Okay. And then if you want to measure ground level and on the center line, then y also will become 0 as I mentioned. So the equation will be very much simplified. I will upload a PPT only with the equations. Okay. That will be useful for your examination. I'll upload and I will show it in the next or in tomorrow also I can upload and send you the link. So you can easily go through the one page PPT. You can get all the formulas in that page itself. I will make it and send you. Okay. So this is a simplified equation. If z equal to 0, y equal to 0, and then if you want to measure the concentration at the ground level, then with the ground reflection, then H also will become 0. Then equation will be very small. So this is your basic equation. You can substitute it. If y equal to 0, then it will become another equation. If z becomes 0, then it will become another equation. So this is your basic equation. Please read this and remain with that. Another question they will ask, because we know the concentration at any point, but they are asking where the concentration will be maximum. That question will come, right? So to find the maximum concentration at what distance and what is the concentration. So we need to find the x at which the concentration will be maximum and what is the maximum concentration. So these two questions will come. For that, I am assuming another condition. The maximum ground level concentration will be at the center line. As I mentioned, it will be a bell shape, and in the y direction also it will be a bell shape. So always it will be at the middle in the sense this line, this dotted line. It will be the more concentrated uh, pollutant. So y should be 0 always, z should be 0 to get the maximum concentration. Then the equation will be like this, as we have already discussed earlier, and you have to get the stability class from the unknown table, like if it's the daytime or night time, and what is your wind speed based on that, and your sun radiation, it is strong isolation or low cloud cover. So usually it will be D class, because uh, uh, based on the maximum condition, it will be in D class only, the stability class I am saying. Okay, then the wind speed can be calculated. If the wind speed at 10 meter is given or the ground level is given, then the wind speed at the chimney's height. Chimney, as we mentioned, 250 meter, 300 meter also it may go. We have calculated last week, right? Based on the concentration of CO2 and the concentration of SO2, we have calculated the chimney height. So if the wind velocity at the 10 meter is given, you have to calculate the wind velocity at the height. Wind velocity will increase with height. That's what we have seen in the first slide. So if it is 10 meter per second here, it will be around 100 meter per second here, or 20 meter per second. Always it will be higher than the wind velocity at the bottom. So that can be calculated by small equation, simple equation based on P. P is the concentration. You can depends on the again stability class. Okay, P you can calculate with which stability class. Based on rural or urban region, you can calculate. So if you want to find U at 100 meter, I need that is my chimney height. Then I know the U at 10 meter. Okay, that you have to substitute, and Z is 100 meter by 10 meter. You can easily calculate power P. Power P you can calculate from the stability class. Then how to find sigma y and sigma z? So we have the chart for both. We have the x. This is a log, semi-log graph. So you have to, if it is 1000 meter, then go with 1000, and you can match with your stability class. Then get your sigma y or sigma z. Okay. Also, you can calculate sigma y and sigma z based on this type of empirical equation. But that empirical equation requires A, B, C, D, that type of coefficient. That also you can get from tables. The theta and all we need from the table. Okay, we will solve some small problem. The stack in urban area is emitting 80 gram per second. So Q is 80. Q is given. It has the effective stack height of 100. So directly effective stack height is given. So H plus del H, that is the capital H is given. That is at 100 meter. The wind speed 4 meter per second at 10 meter. So they have given wind speed at 10 meter only. So we need to find the wind speed at 100 meters. So that is your stack height, right? Effective stack height. So we need the wind speed here at 100 meters. And they are asking us to find, it's a clear summer day. So you think what is the stability class for the clear summer day? With the sun nearly at the overhead. So there is no cloud. And estimate the ground level concentration. So x only they have given, y and z are 0. 2 kilometer downwind the central line. And so x equal to 0, sorry, 2 kilometer, that is 2000 meter. Central line is y equal to 0, z also 0 because it's a ground level. So second is 2 kilometer and 0.1 kilometer away from the center line. So it is 100 meter. So the second condition is this. So 2C we have to find. So as I mentioned, for the stability class, strong insulation because there is no cloud. So at the daytime, wind speed is 4 meter per second at 10 meters. Then you can identify the stability class as B. So if you know the stability class and if you know the distance x, then easily find the sigma y and sigma z. Okay. Then you need to understand the wind speed at the effective stack height, that is 100 meter. So if I know at 10 meter 4 meter per second, then what is for 100 meter with PS 0.15, because for the stability class B urban region it is 0.15. So if I substitute, I will get the wind speed at 100 meter 100 meter stack height. Then I have to substitute my bigger equation. Directly they have taken the x comma y comma z equal to 0 formula. So if you want to put it in the bigger formula, then z will become 0 and you will get concentration as 64.3 microgram per meter cube. They have substituted sigma y, they have substituted sigma x, that is calculated from the graph, and effective height is 100 meter and y is 0 because y and z are 0, and if q is 80 microgram per meter cube, pi is there, sigma y sigma z is there. So this is a formula. Okay. So same if you go with uh, 100 meter or 0.1 kilometer away from the center line, then y will be there. Okay, then the concentration becomes 60.6. You think here 64, here 60. So at the center line it was 64. So if you move 0.1 kilometer away, then it will be a bell shape. So at the center it was 64, here it is 60 only. So if you move around at least 1 kilometer, then it will be 50 or 40. So it will reduce in the downwind and the center line away from the center line. So this is simple Gaussian plume model. It is very simple to calculate mathematically because all the conditions and tables are given. What are the advantage of this Gaussian plume model? So you will produce results that match closely with the experimental data. No need to go and check the concentration at 2 kilometer away from the industry. You can simply calculate based on the wind direction, wind speed, and the stability class. Incorporate turbulence. It everything was incorporated already based on the stability class, and extremely fast you can calculate. Simple, quick, and then don't require any supercomputer. Solving in a single formula that can be used to calculate the concentration at any point, and it is a cost effective method compared to high performance computers. Okay, but what are the limitations with this Gaussian plume model? It will not take into account the time required for the pollutant to travel, because it may take I am assuming whatever emitted will be like this in the conical form, but I don't know, like after 1 day or after 2 days it will reach the 2 kilometer, or on the same spot it will reach the 2 kilometer. That and all not considered in the model and not well suited for the regional model. So it can be used only for the point sources and not able to calculate recirculation effect. It will, we are assuming it's going in the one direction, it's not recirculating because of the buildings or any intersections, and unable to predict concentration of beyond the radius of 20 kilometer. So our maximum distance we can calculate is up to 20 kilometer only. So about 20 kilometer you can't calculate. That is the radius I am asking. Y or Z, X, everything. So for greater distance, this will not work out. So that's what our conclusion. Gas and plume model is very simple, and it's assuming all, it's incorporating all the wind direction, wind speed, and turbulence factors. It's assuming the steady state, and to determine the parameters like sigma y and sigma z, we are using Pascal's Gifford stability classifications to get the stability class, and widely used to estimate the local pollutant level. So hope you understand about the Gaussian plume model. If you have any doubt, please unmute and you can ask, or please post it in the chat box. Because it's a simple model, the only one formula is C x comma y comma z equal to what. If it is on the ground level, then assume y equal to 0, z equal to 0. If it is away from the center line, then there is a value for y. If it is above the center line, ground level, then z there is a value. That's the three conditions you have to incorporate. Okay, simple. Then we are going to model the same for line source and the area source. As of now, we have taken for only the point source. Whatever the pollution happening from a chimney or a industry. Now we are going to look into the line source. Line source means a car or automobile that is emitting pollution. That is a line source. Area source is a group of industry, like a Sipcot. It's emitting in whole pollution as a area source. Then what will be the concentration at a point? This three we are going to model, and what are the alternate method to calculate the area source? This three we are going to see now. Okay. So for the line source, we are assuming the ground level is flat, and we have an infinite length source. One different assumption here is the wind is blowing perpendicular to the line, but in the point source, whatever the pollution is going in the wind direction. But here you can see the car is moving in this direction, that is the pollution emission, but the wind is blowing in this direction. You got it? So that's what the model for the line source models. So consider a road or a highway. X is the direction of the wind, and Y is your pollution emissions. Okay. So if you want to derive for the point source, for the same model I am taking for the ground level concentration, because it's not emitted above 10 meter or above 100 meter. It's emitting at the ground level, because all the exhaust of car or engines, everything will come out at the ground level. So we are taking C equal to, sorry, C of 0 comma sorry, x comma 0 comma 0. So that formula I am taking here. Okay. So y square and h square is, sorry, z equal to 0, and y they are taking as a value. So this expression for the point source will be modified expression for the line source. So, as I told, any model can be derived from a small strip or a small control volume. Here I am taking a small strip because it's a line. So the line, the mass per time length of pollution can be taken as Q equal to Q, small q into dy. That is the pollutant emitted by one car or one particular point in this strip. So that can be calculated from this equation. So that is applied to the concentration of the pollutant formula. Then it is integrated to get the final equation here. So as I mentioned, the line is going in a infinite up to infinite distance. So it's starting with minus infinity to plus infinity. I'm not having any boundary. So it is integrated from minus infinity to plus infinity to get the final equation. So the simplified equation is this one only. This is a simplified equation for the line source model, and you have to substitute s equal to 1 by root 2 y by dy. So you will get the s as a parameter here, and in the final equation will not have any other parameters. So it will be c equal to 2q by root of 2 pi sigma z into u. U is your wind velocity, and only sigma z will be there, no sigma y, because there is no movement from the center line. And q is your small q is your emission per length of pollutant. So that's what we are changing capital Q into small q. You got it? So small q will be, this is microgram per meter cube. So this will be microgram per meter cube per meter or per vehicle. So this is your final small q per meter. So just think about this formula. This is your final formula. And if you always you think the wind is flowing in an angle, then you have to substitute one sine pi. That pi is the angle of wind direction. So if pi is 0, then concentration will become infinity. So always you have to assume pi is greater than 20. That is your wind direction. You got it? Otherwise, if you take any value, it will become 0. Pi will become 0, and the concentration will become infinity. So this line model will be used to find the ground level concentration of any car or scooter emitting ground level pollutant, that is h equal to 0. Then your equation will become this. So line source example is motor vehicle, agricultural burning. Everything is happening at the ground level, but it's a line source. The line of industry source on the bank of the river, then everything is a line source, right? Each industry is emitting in the same direction, then it's a line source. So just for your understanding, there is a small problem here. So estimate the total hydrocarbon concentration, that is your pollutant, at a point 300 meter downwind, that is your x. So I am emitting here after 300 meter, that is x distance, on an express highway at 5:30 p.m. That is your evening, and overcast day. Overcast day, the stability will be D. Stability class you can assume D for the overcast day. Got it? And then the wind is perpendicular to the highway. Then it is a point source. Highway means point source only. You have to anyway assume the wind is perpendicular to the highway at 4 meter per second. That is your U, and 8,000 vehicle per hour. And the average vehicle speed is 40 miles per hour, and the emission rate is 2 into 10 power minus 2 gram per second. You got it? So I have to get small q value. So small q I can calculate by this is the one. Sorry, small q I have to calculate by multiplying the emission from a single vehicle into number of vehicles per meter. So you have to calculate vehicles per meter by multiplying vehicle per hour into miles per hour. Then with the speed and vehicle per hour, you will get the vehicles per minute. Just by seeing the unit itself, you can find. I want Q. Q should be microgram per second. This is capital Q, but I need Q in terms of per meter. So microgram per second per meter. For that, what I have to do? I have to divide it by meter. Meter will be here, miles is here. So vehicle per hour into mile per hour, hour will cancel vehicle per minute. Then you have to multiply here, you will get per miles. That's what the concept here. You got it? Then I have to get the stability class. Stability class is overcast day, that is D stability class. So downwind direction is x equal to 300. So x equal to 300 at D, what is your sigma y? What is your sigma z? Anyway, for line source, there is no sigma y, only sigma z is required. Substitute it in this equation, you will get value 300, 0, will be 42 microgram per meter cube. That is your final concentration of hydrocarbon when it is emitted from the emitted in the express highway. The concentration of after 300 meter will be 42 microgram per meter cube. You got it. Then the area source. Area source is like burning the whole landfill or a group of industries, or again you can say here as agricultural burning. This and all will come under area source. Okay. So this concept of area source become important to facilitate the modeling and predict the concentration. The same we are doing for all the models. Like I have to assume here there is the area of this is the area source, but I am converting this area source into a point source, and I am using the first formula again. That is a point source formula. So how to convert the area into a point? I have to project backwards. Then I will get the point here. So if I am emitting from a point source, then I can easily get a value at a distance here. So if I am emitting from an area source, I am converting it into a point source. Then after the area source, what is the distance here? The total distance I am getting, and I am calculating the concentration at this point. You got it? So this is one of the method to convert area source into point source, and total distance I am getting. But at 300 meter away from downwind direction means this is 300 as I know x. But I have to get the imaginary x, that is x naught here. I have to add this imaginary x and my original x to get the total x. Then I have to do the point source calculation, the same concentration C formula. You got it? So that's what the virtual point. Understand the assumptions represented by equivalent point source. Each of which represent the emission from the small area. Then it will be calculated as a point source model simply. So the distance of the virtual point. Virtual point is the area is converted into a point here. That is a virtual point x naught. Okay. Then the distance between the location where we are measuring the concentration of the area source is xr. The location to the receptor, that is xr. Then the total will be your x. You have to use the model for this x only. Final model will be for this x. And the emission from this point area source is q, and this side is s. So this side is s. Area side is s. I am assuming this is a square. So this will be s. So s is used to calculate the x naught, the virtual point I can calculate. Okay. Then initial spread of virtual point is sigma y naught. See, this is the point. So this is the area source. I am actually requiring the concentration at this point at a distance xr, but I am converting this into a virtual point, that is at the distance of x naught. That's the virtual x direction distance. This is the y naught, that is virtual y naught, sigma y naught. Okay. Now you see the virtual point is taken somewhere back with respect to the original point, and shifted distance is x naught. This is the shifted distance. Actually, the point is here, area is. I am shifting this point to here because it's the area. That is the distance is x naught. How to find sigma y naught? From s by 4.2. That is the exact equation. Sigma y can be calculated from s by 4.2. What is s? S is the side of the area that is emitting the pollutant. If I know sigma y naught, I can calculate x naught, right? How can I calculate x naught? The same graph I am going back. So I know the stability class. I know sigma y now. So if I go back, I can get the x naught. You got it? So it's a back calculation. So I am going backward. I am getting the x naught value. I know the sigma y naught from the s value. I know the stability class. So if I back calculate, I can get the x naught value. It's simple. Then I have to add this x naught and the xr, the total x I can calculate. So this x I have to calculate again sigma y, sigma z, that is the final sigma y and sigma z. I have to substitute in my first equation, that is the point source equation, that will become your area of value. You got it? So the summation is your x naught plus xr. Calculate the sigma y and sigma z for the calculated x naught. Then just convert into normal point load. GPM equation for the point load we have to use. Okay. So only assumption is we are getting a virtual point. That's it. So you just see the example upwind of a Taj Mahal. Taj Mahal is here. Please don't mind my drawing. So there is a Taj Mahal here. There is a industry 30 meter. There is a industry of 30-meter height. Uh, Sending a pollutant acts as a area source. So, okay, towards the national momentum. Sorry, monument. So it's emitting a pollutant as the area source. So the quantity of emission is 100 kilogram per hour, and the mean velocity of the wind is 30 at 30-meter height. So they directly given what is the pollutant at 30-meter height. So no need to convert 10 meter to 30 meter. Directly they have given wind speed at 30 meter. And the side of the area source S is given as 500 meter. So if S is known, sigma y naught can be calculated from the sigma y naught and the stability class. What is the stability class? You can calculate based on stability class. We can calculate the x naught, and they are asking the distance between the these two. If we know, we can calculate the pollutant reaching the Taj Mahal. So treat the area source as effective point source. Modeling will be proceed as it would from the point source located in the center. So you have to calculate the sigma y naught from S by 4 and calculate the concentration of pollutant from the industry affecting Taj Mahal. Okay, taking distance of industry from the Taj Mahal is 4,000 meters. So XR is 4 kilometer. So what is X naught? I can calculate. See, they have taken drawn this diagram. 4,000 I know. S is 500 I know. This is the wind direction. This is the whole industry. So this is Taj Mahal T. So I have to calculate S by 4. I can get the sigma y naught. The stability class what they have given, atmospheric condition E. Is they mentioned the atmospheric condition? Yeah, atmospheric condition of E. So I know the sigma y naught and E. I can get the x naught value. So if I know the x naught value, just see the figure. X naught plus xr will give you the total. Receptor means R, Taj Mahal means T. So simply they have converted. So I get the total X. So if I know the total X, again I am taking sigma Y and sigma Z for the calculated X. What is X? 6,800. So 6.8. What is the sigma Y? What is the sigma Z? Okay. Then I have to calculate the concentration at the downwind direction reaching the Taj Mahal. So I know the height of the Taj Mahal and I know the Y center line only, right? So Y equal to 0. So just put it in this equation, you will get the concentration as 122 microgram per meter cube. I hope you can simply calculate this. If you have any doubt, please reach me out. The initial spread for the intersection of the area source is given as yeah, that's what we have discussed now, ma'am. Sigma y naught S by just put the answer. But please don't discuss the week force assignments here. That I should not supposed to discuss here. So the answer is actually we have discussed here. So sigma y naught can be calculated by S by 4.2 or 4. You got it? Okay, fine. So what is the disadvantages of this area source model? It requires a large amount of input information because I need S value, I need all the values and all. So consume large amount of computer time and involves complexity. That's the problem. So I can go with some alternative methods like narrow plume hypothesis models or using area emission rate models. That and all I can use as an alternate method. So you see here the assumptions for the hypothesis source directly upwind and the area emission rates can be neglected in the crosswind direction and emission rate do not vary. So these are all the assumptions. Simply I am getting the narrow plume hypothesis model. Like series of infinite crosswind lines are calculated and ATDL model, that is atmospheric turbulence and diffusion laboratory model, and regional air monitoring model RAM models are given. See, C equal to K QA by U. K can be 50, 200 or 600 based on the pollutant like SO2 or PM or CO. and QA is the area emission rate, and U is the wind speed. So if you know these three values, simply put and get the area. For the area model, you can get the concentration. So that's the conclusion is point source we can get from the equation, and area source you can convert into a virtual point, and you can use the same point source model. Uh, but there is a problem with the data. If you don't have more data, you just go with the hypothesis model proposed by narrow plume hypothesis. Okay. So we will solve some more problems like practice problem for point source, line source, and area source. So you read this question. I'm going with the question again. This is again a problem solved. Yeah. So sulfur dioxide is the pollutant here. So Q is the rate of emission, 160 gram per second. That is where emission from a stack height of 60 meters. So directly they are given the capital H. Otherwise, you have to calculate the stack height plus plume rise you have to calculate. Then you have to add both to get the effective height. So wind speed at the effective height directly they are given as 6 meter per second. So no need to calculate again the U at 60 meter. Directly they are given wind speed at the effective stack height is 6 meter per second. And atmospheric stability class is capital D. On an overcast day, overcast day means stability class D only. Okay. So they are asking us to calculate the ground level concentration. So ground level concentration is equal to 0 at the center line. So Y equal to 0 at a distance of 500 meters. So X equal to 500 meter. You got it the first problem. In microgram per meter cube is the result unit they require. And the second question, concentration crosswind at 50 meter from the center line. So second question, Y equal to 50 meter and the downwind distance is 500 meter. And the third question they are asking the position downwind on the center line at a ground level where the maximum concentration will occur. So they are asking what is X to get the maximum concentration and determine the maximum value. What is the maximum concentration? C max. So both they are asking us to find. You got it? So how to find? First I have all the data. So for keeping in the bigger equation, I need sigma y, sigma z. To calculate sigma y and sigma z, I know x equal to 500 and stability class D. I can find the sigma y and sigma z. Substitute here with y equal to 0 and z equal to 0 and h is 60 meter and u they given directly for 6 meter per second. So your answer is 65 microgram per meter cube. You got it? Then the second question is y also they given us 50 meter. So substitute y as 50 meter in the same equation, you will get 1.696. See the difference. The concentration is 65 meter microgram per meter cube. But if you move just 50 meter away from the center line, your concentration is reduced to 1 microgram per meter cube. So think about the normal distribution. It's 60. After 50 meter, it is 1 microgram per meter cube. That's what the dispersion happened. It's dispersed a lot, reduced when crosswind dispersion comes into picture. Third question, they are asking the maximum concentration. So the maximum concentration will occur at h by root 2 always. So we know the h value is 60. So we can find the sigma z. From the sigma z, back calculate the x value. So I know sigma z, I know d, that is a stability class. So directly calculate the x value. That is 1300. So for that 1300, I have to calculate sigma y and sigma z. Then substituted the bigger equation. They are asking at the center line. We know center line only will get the maximum value. So 1300 comma 0 comma 0 is your 1300 is the first answer. That is the distance at the maximum concentration we can get. And what is the maximum concentration? 873 microgram per meter cube at a distance of 1.3 kilometer. You got it? Then there is a problem for the point source. So in the point source, we are given with the sulfur dioxide same pollutant at the rate of 160 gram per second into the atmosphere, where the wind speed is expected to be 6 meter per second, same wind speed from the effective stack height of 5.1 meter per second, and the ground at the ground level of 10 meter at the night time. So they are saying like night time at the ground level 10 meter height, the wind speed is 5.1 meter per second. So what is the wind speed at uh, effective stack height, that is 6 meter per second. So you see the difference, 5.1 meter per second and 6 meter per second. And then it is desired that the ground level concentration at the center line is 200 microgram per meter cube. See they given at a distance of 800 meters. X also they given. What is the effective stack height? H they are asking. So just calculate the same use the same formula to calculate the H. So they said night time U equal to 6 meter per second. So the stability class will be D. It's a calm. You know the wind speed 6. Just see here, night time. So always it will be DD. Okay. From the table they will give to calculate. And then sigma is that you can calculate for 8, x equal to 800. So put it in this. Only H is unknown. You can find the H equal to 76 meter. Again, there is a problem for the point source only. A chimney of height is 250 meter, emitting the rate of 500 gram per second, and it is a sunny day and a moderate wind speed. Okay, so you can calculate the stability class. And the stack diameter is 5 meter, exit velocity is 13.5 meter, gas temperature is given, wind speed is given, plume rise temperature is given. That is the temperature at the exit. This is the ambient air temperature. Then the ground level concentration they are asking at the center line at a distance of 1 kilometer. So x equal to 1 kilometer, y equal to 0, and z equal to 0 because ground level. What is the concentration they are asking? Stability class A they given, and the density they are given. So what is the requirement now? We know the x, so we can calculate sigma is that. Okay, we don't know h value. Effective stack height they didn't given, only the stack dia they given because h is missing in that formula. H is required. So for finding that, we are going to use the formula here to determine the effective stack height. So we have the Gaussian dispersion model to find H. You know that value, right? Minus q by sigma is that also we have. But if you don't have that values, only with the temperatures it is given, we can use this formula to find the H value. Okay, how to find the H value? 150 F by U bar. U bar is the wind velocity at stack height. So F is unknown. Now F can be found. F is the buoyancy flux parameter. You know the G value 10. You know the velocity at the exit velocity. You know the diameter of the stack, and then the plume temperature and the ambient air temperature. You know. Substitute, you will get F. So if this type of problem comes, they will give you the formula, no issue. So just understand, if there is no other data other than temperature, you can use this formula to find the effective stack height. Because for the concentration formula, we need what we need? Del H we need, right? See here, the final formula we need capital H. For the capital H, we need the whole effective stack height can be calculated from here. So if you substitute all the values here, you will get the del H. Okay, Vs is pending now again. So volumetric flow rate can be calculated by Vs into AS. Volumetric flow rate is Vs into area, we know pi by 4 ds square. Vs is 13.5. So this formula can be applied only when the volumetric flow rate is 50 meter cube per second above. So it is 265. So it is greater than 50 meter cube per second. Just remember this. This formula can be used only when the volumetric flow rate is greater than 50 meter cube per second. So we know Vs is 13.5, but volumetric flow rate we have to check whether it's above 5 meter cube per second or not. Then you just calculate this formula. Del H is 158. Then the effective stack height can be calculated by 158 plus 250. What is 250? The plume rise. Where it is given? Chimney has a design stack of 250 meter. Okay, that is a stack height. The plume rise, that is a del H they have calculated. Now they have to add both the physical stack height and the plume rise to get the total H, capital H. So see, for a 250 meter stack, the plume is rising up for 158 meter. Then think about there is a chimney and the plume is rising 158 meter, then it's disposing. Then think about how much height it is rising before getting disposed. Okay, then the capital H we have calculated now. We know 1 kilometer, so just calculate sigma z, then put it in this formula. Because I said x they given, y and z is 0. H we know. Okay, just substitute here. We will get the concentration as 262 microgram per meter cube. Okay, the same problem we will solve for line source now. Point source we have we got four problems. One is normal C calculation. One is with all the other parameters as 0. One to calculate H from the concentration. One is to calculate H through some other volumetric flow rate equation. You got it? These are the four problems we had seen in point source. Now line source formula we are going to use for the use to calculate the concentration of pollutant in this. So you can see here the question is given as Delhi Jaipur highway. Here the emission rate is 0.04 gram per second. That is your Q. They given your Q value. So determine the total chemical concentration of the pollutant at a point 500 meter downwind. So if you assume a chimney here, so there is a distance 500 meter away from that. What is the concentration of the pollutant from the highway at an overcast day? So the stability class is D. Please remember, overcast day, stability class is D. Otherwise, they will give you the stability class. Otherwise, the sunny day or a night time, that and all they will give along with the U value. You can get the stability class from the table. Okay, the wind is perpendicular to the highway. Then you can understand this is a point source. It is highway. The wind is perpendicular. So we have to use the line source formula. And the wind speed is 4.5 meter per second. The number of vehicles is 0.150 per length uh, of the road. So you just multiply with the pollutant. You will get gram per second per meter. See, gram per second per meter you can get. That is your small q. Capital Q is microgram or gram per second. But in the line source we need per meter. So it is a small q. Okay. So they given gram per second. Then you have to divide it per meter. You will get the source, emission source. Then get your 500 meter sigma y and sigma z. Sorry, sigma y will not be there in the line source. Only sigma z is enough for the stability class of D because it's a overcast day. Then just substitute in this equation. You know the line source equation. So the ground level concentration, ground level source H equal to 0 because the vehicles are emitting at the ground level, right? So see the emission from the vehicle. So it is ground level. So H is 0. If it is a chimney or the stack, there is a effective stack height, capital H. If it is a vehicle, then it will emit in the ground level. So H is 0. You got it. So just use this small formula. You will get 500, 0, 0. What is the value? C equal to 53.2 microgram per meter cube is your answer. It's a point source. So point source can be also applied to the industries. Having line of industries in the bank of river, then it is also can be considered as a points line source. There H will come in the picture. But if it is a traffic emission, then H will be assumed as 0. Hope you understand that. Okay. Then now you please go with the area source formula. Hmm, 1 second. Okay, sorry for that. So now we are going to solve some own problem in area source. So area source, how you have to convert? There is a S given, that is the sides of the area, and we have to consider a visual point at the back side, that is your assumed x naught. Then we already know what is the point they are asking, that is 1xr. Then we have to sum total. So again you have to use the same point source formula. Okay, just see this question on area source 400 meter. Effective height, stack height is given as 40 meter. That is the area's effective stack height. Okay, and the distance from the source to the residence is 4000. So source from the source to the residence it is 4000 meter. So xr is given, and the mean velocity at the height of 40 meter is 5. So directly they given the u bar as 5 meter per second. So no need to convert 10 meter to 40 meter. They already given the wind speed at 40 meter. If they not given the wind speed at the effective stack height, you have to calculate what is the formula. U bar equal to U into Z by Z bar. Z by Z bar. You got it. Power P. Power P you can calculate from the stability class. So modeling will proceed as from the point source located at the center of central line. So you know the point source located at the central line they are asking. So y equal to 0. So sigma y equal to s by 4, that also they have given. Y naught they are saying. So this is the sigma y naught. Okay. Then yes they given or not? No. Atmospheric condition is E. Then the concentration of pollutant from the area source affecting the residence. They are asking the pollutant concentration at the residence means 4000 meter X they are asking. Okay. Now how to find S? Okay, first itself they given the side. Side as 400 meters. So yes, they given easily. So given S is 100. From the area source to the receptor, it is 4000. So we are assuming a backward point source here. Okay, this is a virtual point. So that is the distance of x naught. So x naught, this is sigma y naught. Sigma y naught can be calculated by s by 4. So s is 400, then sigma y naught will be 100. So for 100, what is the x? Sigma y naught is 100. For 100, at a stability class of D, sorry, E, what is your x naught? So x naught you can calculate and put it in that figure. So this is what is the x naught? 2400. So we have calculated as 2400 meter. Okay. So from the 2400 meter plus 4000, 6400 meter. So total is 6400 meter is the final x. So that is the final x value. Add x naught and the xt or xr, the receptor's value. So if you add both, you will get the total x. Now for the total x, calculate the sigma y and sigma z, put it in the point source formula. That is the first formula, the biggest formula. And they are asking the ground level. So ground level y equal to 0. Sorry, center line y equal to 0. Ground level z equal to 0. Stack height 40 meter they given. Just substitute in the smaller formula. You will get the concentration value as 246 microgram per meter cube. This is the area source formula. Okay. So what we understood now, Gaussian plume model is a simple model and that can be used to find point, line and area source concentrations. If it is emitted from the area source, we can calculate the concentration at any point. C, x, z, y, z, we can find any concentration. Several assumptions were considered like steady state, it's infinity source, wind speed is constant, this ground is plane. This type of assumptions we got, but there are some limitations. It cannot be done above 20 kilometer of radius. Turbulence and all not taken into turbulence are taken into account, but time is not taken into account, and the reactions are not taken into account. So these are all the limitations, but it is giving a good value. Even though it's having limitations, it's giving approximately the good results. So variety of factors like wind speed, effective stack height, and stability class are taken into account. You got it? Yeah. So finally, some two small concepts we are going to see here. One is assimilative capacity. Assimilative capacity is, I think you have studied, if people are from basic environmental engineers or civil engineers, you may know the basics of environmental engineering. In water pollution, we have a concept of self-purification. If you emit any industrial effluent into the river, so the river has its own capacity to treat the pollutant in the river. So by its turbulence and dispersion or mixing with the bigger quantity, it will reduce the concentration. That is called self-purification process of the river. The same is happening with the air. That is called the assimilation capacity of the air shed. So air shed is the total area of the air, volume of air in the city that is having small pollutant. If CO2 concentration is around 300 milligram per meter cube, if you assume, and I am emitting 100 milligram per second, then what is the assimilation capacity of this air shed, the whole area and the volume to take care of my pollutant? If I emit more than the assimilating capacity, then there is a problem. You got it? If I emit less than the assimilating capacity, then the air can purify on its own. That's the definition of air shed. So, sorry, assimilation. So, air shed is a common characteristic of air pollution, emission sources, and wind flow pattern. So, they are saying this as a air shed because this whole area having same wind speed or wind direction or any concentration of pollutant. So, this area is assumed as a air shed. So, this air shed is defined as a part of atmosphere which behaves in a coherent way with regard to the dispersion of the pollutants. Then airshed delineation you see, airsheds are the defined boundaries. There are limited geographical regions such as a small valley and the limited topographic constraints. There is no building or no mountains in within the boundary I am saying. So there is a same wind flow direction without any turbulence. It's called the airshed delineation. So you can see this is a airshed, large geographical area covering hundreds of square meters. So in India, you can say airshed can be a country or a state or a locality. So Delhi, if you see, that is a airshed. They are assuming. So it's a vast, relative level area which no significant change in the land height also. So how to delineate the airshed by emission inventory? That's what we are going to discuss later. And analysis of meteorological data like wind speed, temperature, wind direction and all, and the air quality modeling. if this three can be combined as a airshed delineation, like quantification of emission, collection of representative meteorological data, and predict the air quality. These three are the main methodology for air quality, sorry, airshed delineation. Then now here comes the concept of assimilative capacity. As I mentioned, whatever the pollutant is getting into the airshed, the airshed have its own capacity to purify the air. Okay, so whenever it is discharged into it without violating the best designation use of this air resources. So we can still use the air after emitting this much of pollutant. Like even some river have some pollution, we can still drink the water. So that much quantity it has its own purifying capacity. The phenomena governing the assimilative capacity of the air environment include dilution, dispersion, and deposition. In water, there is a turbulence and deoxygenation, reoxygenation will happen. The same in air, dilution, dispersion, and deposition is happening. Because of that, the pollution is getting reduced, the concentration is getting reduced. So what is the use of assimilative capacity? Why we have to find this? So if you find this, then you can understand whether the air is good to breathe or not, like safe limits of disposal of pollutant, whether I can add some industry or not. If I know the concentration in the air shed, then I know, okay, this is already exceeding the air shed, assimilative capacity. I should not construct any industry in this air shed. You got it? Then if there is any industry in this air shed, if it is having less assimilative capacity, then the pollutant will add up, and that air cannot be used for breathing, even for breathing. So that is the indicator for indication of potential for future growth, whether any industry can come or not. So we can have estimate by two approaches. One is with ventilation coefficient. The second one is with the pollution potential or dispersion potential. So the two assumptions only. One is assimilation capacity is directly proportional to the ventilation coefficient and indirectly proportional to the dispersion potential and the pollution potential. That is the two concept here. So how to find that? As I mentioned, the wind speed will increase with the height. So at ground level, there is no wind speed. If you go above the mountain, the wind speed will be higher. That's what the concept, basic concept here. So the product of mixing height and the average wind speed will give you the mixing layer. Within the mixing layer will give you the air shed. Got it? This is your air shed. So I have to draw a diagram with the u as a x-axis, and that is the wind speed in the x-axis and height in the y-axis. Then if I multiply the u and h within the mixing height, I will get the ventilation coefficient. So the product of mixing height and the average transport wind velocity within the mixing layer. Then the ventilation coefficient in an atmospheric condition, which gives an indicator of the air pollution dispersion, ambient air quality, everything we can get. So higher the coefficient, the atmosphere can easily able to disperse and dispose. If the coefficient is lower, then the wind speed is lower. It's directly proportional to wind speed, right? So if the ventilation is lower, poor dispersion. So there is no ventilation. That's the concept. Stagnation of pollutant is happening. So how to find the mixing height now? Because we have to multiply the u and z within the mixing height, right? So how to find the mixing height? So mixing height is based on the height of the layer in which the pollutant are vertically dispersed. Above that, there is no dispersion, right? So it determines the volume of atmosphere available for the dispersion of pollutant. Above that, there is no dispersion. So you see here, this is the mixing height. Above that, there is no dispersion. The pollutant is trapped within this layer, within this height. So how to find the mixing height? By radius sounding, remote sounding methods or parameterization models. That and all we can use to find the mixing height. See there is a problem to find the ventilation coefficient. So how to find the ventilation coefficient? You have to multiply Z and U within the mixing height. So first find the mixing height. Okay, so the ground level air temperature is 15 degrees Celsius and the normal maximum surface temperature is 26 degrees Celsius. You see the ground level, the temperature, air temperature is 15 degrees Celsius and the surface temperature can go maximum up to 26 degrees Celsius. You got it? So they are asking at an elevation of 100 meter and 300 meter, the temperature is 17 and 21. So just draw a line. So at 100 meter, the temperature is 17. At 200 meter, at 300 meter, the temperature is 21. So draw a line. So this is linear or any pattern it will follow. See 15, 17, 21, it's following a pattern. Then the wind has a velocity of 2 meter per second at 10 meter above. So wind direction is this. So wind speed is 2 meter per second at 10 meters. So it will vary. So again, the wind profile will be a parabolic profile, right? So wind at 10 meter it is 2 meter per second. What is at 100 meter and what is at 300-meter height? That and all we don't know. So the wind exponent is zero point 0.3. That also they have given exponentially it's varying. The exponent is zero point 0.3. It's a parabolic or exponential variation. Calculate the maximum mixing depth. Mixing depth is the mixing height. And then the ventilation coefficient. Ventilation coefficient is U into Z. So this sum we can do in Excel only. So they have already done and given this. So 1721 and all at 100 meter and to 300 meter height. What is the temperature? And we know the maximum temperature of the surface can go up to 26 degrees Celsius. Draw a line, that is a inclined line at an that should meet the actual ELR. ELR is environmental lapse rate. So that meeting point is your maximum mixing depth. So how to draw this line and at what inclination this angle should be there? That is based on your lapse rate. So see here, it's a 21, it's 17 degree by 300, 100. These are all the depth. So you know difference in temperature by difference in altitude, it will be your lapse rate, right? Del T by del Z your lapse rate, that is theta. So that will give you 0.02 centimeter C by M. But this can be drawn with the DALR. We know dry adiabatic lapse rate is minus 10 degree per 1000 meter or 1 kilometer or 0.01 degree Celsius per minute. So that you can draw a line wherever it's meeting the intersection. That is called the maximum mixing depth. The air person will rise until that intersection. Above that, it will not intersect because it's going as an inversion, right? So up to that, it is a unstable condition. So it will mix. Above that, there is a inversion. So just find this point. How to find this length? So we know this two slope. One is 0.02 centimeter degree Celsius per minute. Another one is minus 0.01 degree Celsius per minute. So I know that two are going to intersect. So at intersection point, both the values will be at the same Z. So 15 plus that is 15. If it is reducing in 0.02 centimeter per second degree Celsius per minute, and 26 if it is reducing at minus 0.01 degree Celsius per minute, then at what point it will mix? That Z you can calculate. Got it? So Z is 366 meter, it will merge. So at 366 meter, that is the mixing height. How to find the ventilation coefficient? It is a multiplication of wind speed and the height. So you can calculate the wind speed at different points. They given the wind speed at one point. So you just calculate the wind speed at different heights. So up to 366 you can find, you can draw a graph, just multiply this area, you will get the ventilation coefficient. MMD into average wind speed. Or else you can get an average. So this is the average. This is the wind height. So this is the area you can simply take. So instead of taking a parabola, they are taking an average value. So that average value into this taking as a rectangle and they are multiplying. So MMD into average wind speed will give you the ventilation coefficient. So there are lots of case studies like Cochin, and they're all doing this assimilative capacity study, and they have suggested whether any industry can come or not to their area. That's what they have identified by calculating the assimilative capacity. So the industrial growth scenarios and different scenarios they have assessed without any industry. If there is new industries, it is coming, what are the impact to the air quality, that and all we can identify. So that is called the available assimilation capacity. There is a standard given by the national air quality for if you are taking a pollutant as SO2. So we know the standard for SO2. Okay, for the urban area. Then we have the ambient pollutant concentration. So if you subtract this two, if it is already the limit itself 100 microgram per meter cube or milligram per meter cube for SO2, and we are already having the ambient air quality of 990 microgram milligram per meter cube, then only 10 milligram per meter cube is available to assimilate, right? So more than that I cannot emit. So if it is only 10, I should not emit more. See, there is a concept for SO2. SO2, the permissible limit is 50 only. So you have to have at least 25% as a backup. So only 75% you can available assimilation you can use. Above that you should not use. See, they have a value of 50 microgram per meter cube already emission rate. So they have calculated and just they have given a conclusion that the industry should not come. This was model you can see here the power plant has a very high permissible emission load at a stack height. it is higher than the minimum mixing height, suggesting the pollutant will travel longer distance and dispose over. They suggested the power plant can come because it's having a larger height of 180 meter, so it will dispose the pollutant anyway before reaching the point. So it's having assimilation capacity. That's what the idea we got. Okay, so final concept is emission inventory. Inventory is the is the point of data collection and modeling. So whatever the air quality we can monitor, and then emission inventory we have to do. Then we have to model that will give you an idea for policymakers to make a control strategies. Okay, so like a comprehensive stock of all pollution emitting sources we have to identify. That is called the emission inventory, the data collection. See, there is a quantification, there is impact assessment, there is a development of policy, and then implementation of emission projection, emission monitoring. I am projecting before the industry comes. I have to calculate it's like an environmental impact assessment. I have to know what are the concentration it's going to emit. Then I have to project the emission, model, and with that model I can say it's okay or not. That's the role of emission inventories. Okay. Then with that emission industry, I can just quantitatively analyze the emission, plan the policy, develop a pollution control strategies with the reduction measures and air quality modeling I can do, and the future projections I can do. You got it? Okay. Then this four I told you, right? Sorry, this six that I am going to discuss. The quantity understanding is like for promoting the better understanding. I need to know the emission inventories, raising the awareness, major emissions. So if it is earlier, it was mentioned that only due to vehicles all the pollutions are coming. But after doing emission inventory, I could know what is the source which is causing the pollutant. Only NO2 is emitting more from the vehicles, but carbon dioxide and sulfur dioxide are emitted more from the industries, and carbon dioxide are emitted more from the flights, and particulate matters are emitting more from the volcano emissions. So these are all the source identification can be done only with the emission inventories, and the priority can be given for emission reduction. This is the overall concept. Then modeling activity, I need input data for all the models. For that, I need to have the U value, meteorological data, and the base background air quality. So for that, we need to do emission inventories. Then for future projections, I need to estimate the future emissions. For that, I need the emission inventory, and the possible reduction measures can be framed with the cost-effective emission reduction measures. Like if I know the particulate matter is from only one industry with the emission inventory data, then I can understand what is the cost-effective method to remove that particulate matter alone in that industry instead of going with the overall air pollution control measures. And then plan policies. It will help the policymakers to develop some measures to control and to suggest. And emission inventory in air quality modeling, you see there is a grid type model is for the India for black carbon. They have found a grid shaped model. With that, I can understand where I can get the where I can there is a more black carbon concentration. So using the dispersion model, I can find this is a there is a two approach like bottom approach and bottom up, then top down method. With the bottom up, you can go with the specific data, then emission inventory, then uncertainty will be reduced. But here you can see from the emission, they are finding the emitted values scaled to the inventory data. Here uncertainty will be higher and like less accuracy. Okay, then what are the pollutants in emission inventory like acidifying pollutant, toxic pollutant, persistent organics, greenhouse gases, and heavy metals? These are all five different common pollutant that can be used in the emission inventories like acidifying pollutant, toxic pollutant, persistent organics, greenhouse gases, and heavy metals. How to find the emission? From the emission factor into activity data. How to find the emission factor and the activity data? Activity data is what are the emitters like the source like transporter, crematorium, power plant, waste burning, biomedical waste, diesel generator. These are all some of the activity that are all the source that is emitting the air pollutant. Emission factor is EF that can be calculated. So actually the definition is it's an average representative value that attempts to relate the quantity of air pollutant released to that person due to particulate activity associated. So EF is expressed as a mass of pollutant divided by volume or weight of a raw material. So microgram per kg. That is mass of pollutant by weight or volume of raw material. That is your emission factor. You got it? Then emission inventories can be of four types: annual, seasonal, forecasted, and grid type. that already we have discussed. The annual can be useful for some areas like US greenhouse gas emission. This type of climate models for the global emissions, we can use the annual average emissions. Seasonal emission you can do for regional activities like they have calculated for China. They have come up with some results like secondary sulfate concentration and rice road dust and building cement materials. And they projected like in this season this is higher more like forecasted and future projections. Like you see for modeling you can use this emission inventories. Finally, grid emission, as I mentioned earlier, so you have to collect the data, digital data generation, and mapping and modeling. Finally, emission inventory you will get. This is one type of emission inventory. And guidelines we have like European Monitoring and Evaluation Program, Intergovernmental Panel on Climate Change, that is IPCC, and then UNDP program, and that is framed by United Nations, and the Global Atmospheric Pollution Forum. They have given some guidelines for emission inventories. So they each guidelines that talks about some combination of pollutants, and they are applied for different places like a long term. If you want to find the long range transboundary air pollutions, like different areas and the geographic location and different aims, we can adopt different guidelines to for emission inventories. You got it? Yeah. And this four emission, yeah, major sectors as we mentioned, that is all receptors, sorry, sources like transport, agricultural, burning, industries, power generation. These are all different sector emitting pollutants. So if you can see, there is a emission inventory example for Delhi. So they have calculated that PM10 value, calculated by different publications. You can see they have mapped it sector-wise contribution. So what are the other what are the sources that is contributing to the PM10? So emission inventory is a prerequisite requirement for the chemical transport modeling and dispersion modeling. So extensive data required, that is very important to do the inventory. And then grid emission inventory will substantially improve the spatial and temporal allocation of emissions. So this is fine. It's a small concept related to air quality dispersion and emission inventories. And the major is the Gaussian plume model and with point source, line source, and the area source. I hope you all got today's lecture. If you have any, sir, can you explain the graph which is used for calculating the concentration of pollutant at 600-meter downward? Okay, so you are asking about the concentration 600-meter downward. Can you please tell me the page what you are talking about? Okay, here. Okay, any graph I will take just. Okay, okay, 600-meter downwind. If it is 600-meter downwind, then x equal to 600, right? That's what you are talking about. Then in the graph, I will go with the x equal to 600. So it is 10 power minus 1, 10 power 0, 10 power 1. Then it is 10, then 1000, 100. So above that, 600 will be there. So go to 600, then just move above, and you know the stability class A, B, C, D. If it is a D, then go with sigma Y and sigma Z. You got it. This is the way we have to calculate the sigma Y and sigma Z for from the graph. Or yes, ma'am, you want to talk? Sorry, sorry, sir. Amara Ahmed. Yeah, ma'am. Um, I will go with the question what you are talking about. 600 meter downwind. No, 800. I couldn't hear you, ma'am. Sorry, sir. Uh, I couldn't hear you. Can you please text? No. Okay, one second, one second. I will change my audio settings. Yeah, it's in headphone only. Speaker also. Yeah, ma'am. Can you talk now? Sorry. Now I got it.
So in these slides, these examples, no, which you have taken,
Yeah,
in
yeah,
this, it is solved for 300-meter downwind.
yeah, yeah,
Sigma Z
ma'am.
value has been calculated.
Yes,
And if we have like 600-meter downwind, then how we will calculate means how we'll find the Sigma Z value in these graphs?
the one I am showing here.
Yes,
This
sir.
okay. So here you can see around this is kilometers. So you can see it is 500 meter. So that is a zero point 0.5 kilometer. So think about this is one. So zero point 0.5 will come here. Got it? It's kilometer. Hope you got now.
No, sir.
You are asking about 600 meter, right? Downwind direction.
Yes, yes, sir.
So it's
Means
zero
if we
point 0.6.
means
It's here.
we want to
0.6.
calculate the concentration of pollutant.
Okay. C at 600 meters. Okay. Then Y and Z are zero, right? What it's around it's in the ground level and in the center line means y and z are 0. Then the formula will be the same formula with y equal to 0. Then this component will go only q by pi u sigma y z and the whole thing will be there. H you can have. So sigma y and sigma z can be calculated from this by 600 meter means uh, hello. Yeah, ma'am.
Sir,
Yes,
Uh,
sir.
yeah, ma'am.
sir, sir, I want you to you're taken a question, okay, a problem,
Ma'am.
and I
So,
want you
how
to
we'll
show
get the
it.
value of sigma Z then? Like,
Uh,
okay,
same, same, same,
sigma Z from,
same. This graph. Sigma y from this graph, sigma z from this graph.
so like sigma Z will come like in the x-axis.
No, no. Every x-axis will be your x distance. Y-axis will be your sigma
Okay,
y. In this graph, y-axis will be your sigma z.
okay. So, sir, can you just explain like how we'll be able to find out that value? Actually, your screen is not like visible
Oh, you.
clearly.
Oh, I'm sorry. Like again, I will go with this problem then. I will take a problem then. Ma'am, you are also talking the same or
Sir,
uh,
sir, I want you to relate the
uh,
question. See,
yes,
there
ma'am.
is a question
Yes.
which is asked. Okay, then you have solved it.
Yeah, ma'am.
You're talking about sigma y, sigma z,
Yeah, yeah,
and
yeah, yeah.
all the axes, right?
Yeah, ma'am.
I want you to, as you are solving, please relate it with the graph, so that no, we'll be
Okay.
able to
So,
connect. I'm
okay,
not
then
able
I
to
will
connect it.
show you the graph itself directly. That you can see the graph.
So
I will.
this is the
Uh,
graph, but
uh,
now the relationship between the question and the answers which you have got. Please
okay.
relate it with the graph. Then we'll
Okay.
understand
Okay.
better.
I think you are confused with the semi-log, I guess. Okay.
Yes,
Now
sir.
I
Yes,
will.
sir.
Yeah.
Yes, sir.
That I will tell you how. Okay.
Okay.
See here. The value is 10 power 1 is 1. 10 power 2 is 100. 10 power 3 is 1000. It's not the simple graph. It's a semi-log graph. So it will extend in exponential way. So 100, 1000, 10,000 it will go. And the same x-axis also in semi-log form. So it is 0, 10 power minus 1 is 0 and then 10 power 0 is 1, 10 power 1 is 10 and 10 power 2 is 100 kilometers and sigma y and sigma z are in meters. So I want to know sigma y and sigma z for 500 meter downwind direction. So x is 500 meter. So for relating into the graph, I need to convert it into kilometers. So it will be zero point 0.5 kilometer. You got it. So both the graph, I have to go and check with the zero point 0.5. So see here, zero point 0.5 is between 0 and 1. So here there is 10 needles you can see. If it is 50, then it will be between 50 kilometers, 5 kilometers if you want. It will be around between 1 and 10. You can see 10 needles in between. So it is exponential again. So there is a large distance here, small distance here. It's a semi-log graph. You can see the same thing in soil mechanics for what do we say that grain size analysis also you can see the same graph sheet, the same graph you can see here. So I'm talking about now 5.5 kilometers. So it's between 0 and 1. So you read this 1, 2, 3, 4 and the fifth one you can see here. So at the fifth axis I'm taking. So it's a stability class of D because it is overcast day or stability class D. So I can directly go into the y-axis. This is the value. So what is the value here? It is between 1 and 100. So 1, 2, 3. It is around 3. So that is 30, right? 3 is 30. 1 and 100. First is 10, second 20, 30, 40, 50. 100 it will be. If you read this one, it will be 200, 300, 400. You have to read up to 1000. If you are reading here, it will be 2000, 3000. You have to read. That is the semi-log graph. You got it. So now I am getting the third one between 10 and 100. Sorry, it's not 1, it's 10 and 100. It will be 36.5 meters. I hope you understand. Or you can take 30 or 35 as a approximate value. Same if you come with sigma z, I am taking the same 0.5 and going with the d value. It is between 10 and 100 at the first point or the between first and the second point. So they are taking 18.5. Hope you understand now, ma'am.
Uh,
Uh,
Sir, I have, sir,
Yes, sir.
in the distance downward kilometer x, the first graph, log
yeah,
bar
yeah,
graph,
yeah.
you said this 10 to the power of minus 1 is 0, right, sir?
1 by 10 is zero point 0.1. Sorry, not 0. I'm sorry. It's 0.1. 1 by 10. That is 10
So
power minus 1.
1 by 10 is 0.1. So
0.1.
the
It is
next
between
number is
the
2, the 3, then 4, then 0.5.
no. Point
Point,
1, point 2, point 3, point 4. Like that. Point 2, point 3, point 4.
no, sir, we are having 500 meters, which is 0.5 kilometers, right,
Kilometer.
sir?
So first
Ah,
first is itself point 0.1. This is
uh,
itself point 0.1. So this will be point 0.2.
point 0.3, point 0.4, point 0.5. Point
Yeah.
0.5 you take it vertically
Taken.
upwards,
Yeah.
and then okay,
So
fine.
if it is 5 kilometer, where will you take? This is 1 kilometer. Then this is 2, 3, 4, fifth kilometer I have to take. Five
Okay, fine,
kilometer,
fine, fine.
and I have to take here. So they
Uh,
have taken for 6,000 meters, right? 6,000 is 6 kilometer. In the next problem, I will go to there. This is point 0.8. Somewhere we have taken around 6,800 and all. Bigger value for x. Yeah, here the total x we have calculated, right? So this
okay,
is
sir.
6,400. So 6.4 kilometer. So see, this is 10 power minus 1 is 0.1, 10 power 0 is 1, 10 power 1 is 10. So mine is 6.4. So it is between 1 and 10.
Yes, sir.
So 1, 2, 3, 4. Sorry, this is 1, 2, 3, 4, 4, 5, 6. So between 5 and 6, I'm missing one. 1, 2, 3, 4, 5, 6, 6.4. It's between,
Oh, this is 5.4 then.
yeah, this is 5.4. It's wrong. Yeah, this
It
is
should
wrong.
be 6.4.
6.4.
It
It
should be.
should be
Okay.
6.4. It should come here.
Okay.
It
Okay.
should come here and it should match here. So what's the sigma y value then? This is 0.1, 1. Sorry, it's a 10, 10 power 1, 10. And 10 power 2 is 100. 10 power 3 is 1000. So it's between 100 and 1000. So you have to read 200, 300. So you read this is 100, 200. So 300. It's between 200 and 300.
So, sir, so sigma y starts with 0, 10, 100, 1000. But
No, they
whereas,
have actually they have given a zoomed graph. So you can get the below values also. But this value starts from 10. So
okay, so
this
10,
sigma z you
10
can see
here.
sigma z you can see 0 to 10 it's starting. But here there is no value you can see. Only it starts with the 0, 10. Below that it will be 9, 8, 7, 6 and it starts with the 1.
Starts with 1. Okay.
Got it? Yeah. So here also it starts with the 10 power 0, 1. 1 to 10. Everything starts with the 1 to and the model will work up to 20-kilometer radius, right? So that 20-kilometer means you can see x is around 20 kilometers. So 20,000 meters. Up to 1 we can use the Gaussian dispersion model. Okay. So ma'am, you got it?
Okay, sir.
Yes, sir.
Yeah.
Thank you,
Thank
sir.
you.
Thank you,
Thank you.
sir. Thank you, sir.
you can solve all the problem. They will give you the graph. I can upload the graph. Actually, there is a big graph. I will show you the exact graph. I'm taking that only. 1 second. I will show you. I have the. I'll say Google it. This is the graph, actual graph. You can read this clearly. Yeah. Here you see the values are actually noted. This is in the max standards. So A is what conditions and all given. So if you want to take 5, you can easily take 5 in the sense it's around 100 to 1000 they are giving. Then 1000 to 10,000 like that the x direction. So if you want to make it, it's a meter. It's in meter. That's what Sarah mentioned in kilometers. So the actual graph will be in meter. So you can easily identify 200 meter, 500 meter, 5000 meters. So just multiply with the 10 power 3, you can get this a single value that you project. So this is also in meter. You got this graph, this will be easier.
Sir,
Yeah.
for exam,
Yes.
will you be providing us with the graph
I think there won't be
to solve?
complicated questions in the exams. I think they will give you the sigma y, sigma z values if it is an exam, I guess.
Okay, sir. Thank you, sir.
That
Because
will be
we have
the,
to be
yeah.
provided with the graph.
Or else they
Yes.
will give the graph, I guess. Give you the graph in the sense in the diagram itself in
Okay.
the question. Yeah, like that. So I
Okay.
can see one question here. A lot of vehicles are okay. Okay. So yeah, lots of vehicle traveling daily releases harmful. I don't know. This is a question from this assignment. So just I will skip here and we will solve the old assignment problem. Just go with this. Yeah, I'll read the questions. You just post. If you have any doubts, please post it in the chat box. You can post the answers in the chat box, say like A, B, C, D. I'm reading the question. What is assumed in the Gaussian plume model regarding the time required for pollutant to travel to the receptor? So we have lots of assumptions in the Gaussian plume model, but the time required to reach the receptor is based on wind speed variation, molecular diffusion, buoyancy effect, steady state. I'm talking related to time. This is one of the limitation also because we have not taken time into consideration because we are assuming the concentration with respect to time is zero. What is that? Del where can I find? Concentration with respect to time is zero. What is this condition? Steady state condition. That is what our assumption, right? So the answer is steady state. Because regarding the time, the pollution will not vary, the concentration will not vary. Only the variation is due to dispersion of the pollutant. We are assuming the 10 meter per 10 milligram per second is emitting every time it's the same concentration. So it's not varying. And if you see here, it's around 100 microgram per meter cube. Here it is 10 microgram per meter cube. That is same every time. That is what the steady state condition. Okay, so the answer D is correct, ma'am. Okay, that's what the assumption here. Time required for the pollutant to travel from the receptor is neglected. So we are assuming this is a steady state condition. Other assumptions are, so this assumptions I got one question in the gate. That's why I'm stressing here. Like it's due to molecular dispersion, no diffusion in the x direction. X direction only dispersion. Sorry, the movement due to wind direction. Y direction and Z direction is due to turbulence. That's why the concentration is reducing in the Y and Z direction. In the center line, it is maximum. Uniform continuous emission rate. Wind speed is constant. Terrain is flat. And the shape of the plume is conical. These are all assumptions. Conical in the sense, again, normal distribution. Center line is maximum. Sides it will be minimum. And no deposition, no reaction. This is one of the limitation. Okay. So second question I am reading. What is an advantage of Gaussian plume model regarding its response time? slow response time, immediate response time, time consuming calculation, dependence on supercomputers. They're asking about the advantages of Gaussian Plume model, GPM. It's a slow response model, immediate response model, time consuming calculation, dependence on supercomputer, because it's a simple equation, right? The concentration at x comma y comma z equal to, they are simply calculating with the what is the quantity and what is pi. I think sigma, there is a value here. Sigma pi 2u will be there, that is the wind velocity, sigma y, sigma z. Then open a bracket, sigma y component will come here with the h, sigma z component will come here with the same h by 2y will be there, right? 1 by 2, 1 by 2, this addition will be there. So all the parameter we know, just put it in the Excel or simple mathematical calculation you can get. So it's a immediate response model. Answer is immediate response model. So quicker than a numerical model, it's extremely fast, simple in their mathematics. That's the advantage of Gaussian flow model. What is the assumed ground concentration in deriving the expression? This was I have stressed again. What is the assumed ground concentration for pollutant concentration from a line source? If it is a line source, earlier we are talking about the point source. If this is line source, what is the ground level? It should be a surface ground level, because H will be 0 always for a traffic emission. That's what ground level surface we are emitting the pollutant. So expression for pollutant concentration from line source will be, ground condition is H equal to 0, ground level surfaces. You got it? Okay. So this is a ground. The assumption for the line source model is ground level surface, and the line what I told, the emission is this direction, but the wind is in the perpendicular direction. This is the y, this is x. But in the point source, if you say the chimney is emitting a pollution, this is the x direction, and the center line, the y also will be in the same axis, it will be, right, and the z will be here. But it is a line source, it will be perpendicular, the wind will be perpendicular, because here the wind will be in this axis, and it is blowing to the infinite axis. The emission is happening minus infinity to plus infinity, and the wind blowing perpendicular to the line. These three are assumptions for the line source models. Okay. So, okay, you want to solve that problem? We will do that problem at the end. Yeah. So, in what direction is the wind assumed to be blowing to the concept of line source that I have already discussed? It is perpendicular to the line. Yes. Now, the equation given below is valid. This question you please answer. The equation given below is valid for calculating the volumetric flow rate. So this is the equation given, right? So this is used to find the volumetric flow rate Vs for unstable or neutral condition. So all the parameters they given, but only the volumetric flow rate is greater than what? Vs should be greater than which value to find the buoyancy? So if you get F, we can get del H. So if you del H, then H equal to, you can get from physical stack height and the plume rise, that will give you the effective stack height. So the answer is 50 meter cube per second. Sorry. Yeah, 50 meter cube per second. It should be greater. Which one? Vs should be greater than 50 meter cube per second. Then only this formula you can use. This formula is valid. Okay. See, the determination of effective stack height, del H formula, can be valid only when the volumetric flow rate is greater than 50 meter cube per second. What is the potential consequences of low ventilation coefficient? We have talked about ventilation coefficient, that air delineations and all. So potential consequence, if the ventilation coefficient is high, then there is a good dispersion. If the ventilation coefficient is low, then there is poor dispersion and stagnant and poor air quality. You got it? So option B is correct. So stagnation and poor air quality. So higher the coefficient, more efficiently disposing the pollutant. If it is a lower ventilation, then poor disposal and stagnation is happening. So seventh question, if you see, the height of the layer in which the air pollutant or any constituent emitted or entrained into its vertical disposal due to the turbulence and convection is called. So the height of the layer up to which the mixing is happening or the vertical disposition is happening. Above that, it's not happening, only trapped in this layer. What height is this? Mixing height. It's a mixing height, right? It's a mixing height. Above that, up to that, there is a unstable condition. That's why the mixing is happening. Above that, there is a inversion condition. Above this, there is a inversion condition. The pollutant cannot escape that. It will be trapped in the unstable layer. So the mixing height is the height of the layer in which the pollutant emitted or entered into is vertically disposed or vertically disposed. See, up to this there is unstable. Above that there is an inversion condition. Available assimilation rate. We are talking about the air assimilation, right? So air can purify on its own. Up to which, how can we calculate the available assimilation? So we are already having a background concentration. We have a standard. So if you subtract this two, you will get how much pollutant you can still emit. So that's the available assimilation capacity, AAC. That can be calculated with the NAQQS stand. It's a AQS stand, National Ambient Air Quality Standard. Minus, if you're taking for CO2, my standard is 100 gram per meter cube. As say, I'm saying just 100 gram per meter cube. So my ambient pollutant concentration already I'm having 50 gram per meter cube. So 75% I can allow. So for 25% I have to keep a cap for the future. So 75% means 75 gram per meter cube I can allow, right? That is the total assimilation capacity. So 50 is already there. So I can construct the industry to allow up to 25 gram per meter cube emission, or a SIPCOT I can allow. Above that, there should not be any emission. Then the assimilation capacity will be lost. That much only available. Okay, that's the important of finding available assimilation capacity, AAC. NOx standard minus ambient pollutant concentration. So the answer is A. Yes. So this is the available assimilation capacity. It's determined by its difference between permissible and the existing pollution concentration. What is the basic equation for emission estimation? So emission equal to emission factor into activity data, right? Emission equal to emission factor into activity data. Yeah, emission factor can be calculated with what are the sources and sorry, that is the activity. Emission factor can be calculated with three models. Then emission, what does the emission factor represented in context of air pollutant? What is that they are asking? Random emission data, mass of pollutant released per unit volume of raw material, dispersion coefficient, gridded emission inventory. What is emission factor definition they are asking? It's a mass of pollutant per volume. I told you, right? Milligram per meter cube or milligram per ton of air. See, emission factor is expressed in as a mass of pollutant divided by volume or weight of a raw material. Okay, one more last question. What are the limitation? What is not a limitation of Gaussian flow model? It is not taking into account the time required for pollutant to travel, not able to calculate the recirculation effect caused by the obstructions like buildings and all, unable to predict concentration beyond the radius of 100 km, not well suited for regional modeling of particulates, mostly due to simplified treatment of secondary aerosol formation. Can you answer this question? All are limitations only, but which is wrong? Which is wrong? Is unable to predict the concentration beyond the radius of 20 km, not 100 km. About 20 km, we cannot use the Gaussian flow model. Right? That's what given. Unable to predict the concentration beyond the radius of approximately 20 km. That's one of the limitation. You got it? So, I will also discuss the question that is asked in the chat box. We'll go with the fresh page. Discord. New slide I will add. I'll project. I'll take. Just see here. A lot of vehicle traveling daily releases a harmful chemical emission. Okay, that's a standard. This given. Consider the average emission rate. That is Q. And if it is a vehicle, you have to think that is a point source, line source, or area source. It's a line source because it's the emission from a traffic. So it's the line source. So whatever is emitting, the wind is in the perpendicular direction. Then the Q is given as 0.05 gram per second. But for line source, what is required? Small q. That is gram per second per meter. So how to find this? Determine the total concentration, chemical concentration of pollutant at 600 meter downwards. So I need to calculate the concentration at 600 meter downwards. So 600 meter is the x downwind direction. So it's a highway on a overcast day. So they said the stability class is D. Okay, that is okay. Let the wind be perpendicular to the highway. That is also already known. With the wind speed of y equal to, u equal to 5 meter per second. That also known. Given. The number of vehicle per unit length is 0.18 meter. So if you multiply 0.18 vehicles per meter, you will get 0.05 into 0.18. What is the calculator stake? I'm sorry. 0.18 into 0.05. This is point, what is the value? 009. Now gram per second per meter. That is small q. What is the C formula? That is a ground level. So y equal to z equal to 0, and in the center line of 600 meter downwind. So they didn't given any distance away from the center line. So y equal to 0, z equal to 0. What is the formula? Can anyone tell the formula, please? For the line source, I'm asking. I'll go with the line source formula. Area source, area source, area source. Okay. So what's for the line source? Yeah, this is the answer, right? C equal to C of x comma y comma z equal to 2 small q divided by root of 2 pi sigma z into u into e power, that is exponential of e power I am talking about, or exponential of minus h square divided by 2 sigma z square. What I told, h is 0. So if it is become 0, e power 0, it will be 1. So this term will get cancelled. So only you need q, u, sigma z. So 2 into 0.09 we know, 009, and divide by 2 pi we know. U is known, 5 meter per second. How to calculate sigma z? That's what you have asked, right? So it is 600 meters, so 0.6 kilometer at the stability class of D. What is the sigma z value? Can anyone tell, please? What is the sigma z value? Can I go to the PowerPoint again? Okay, I'll move. I'll check for sigma z for 0.5. So 1, 0.1, 0.2, 0.3, 0.4, 0.5. Stability class of what they given? D, right? Stability class of D. So this is matching here. So 10 power 1 to 10, 20. So I am taking value of 20. Sigma z is 20. What is the unit for sigma y and sigma it is? It's meter. So if you take out everything, it will be coming in. Uh, what is the q in gram? So gram per meter cube it will come, because this is meter. This is meter per second. This everything will cancel out, and this is a meter, so everything will be in gram per meter cube. So what's the answer here? So convert into 10 power minus 3. You can take as microgram. 2 into 0.009 divided by 20 divided by 5 divided by root 2. Root 2 is okay. Value is 0.0018. 0.018 divided by root of 2 pi. What is root of 2 pi? 2 into pi, then square root of that value will be 2.51. So 2.51. So what is the answer? 0.00018 divided by 2.51. So if it is converted as 10 power minus 6, that is 0.7. This is coming 0.7 microgram per meter cube is the answer. Is that in the option? Is there any option related to 0.7? I think Mohanty, Shubhankar Mohanty. This is the procedure. You can calculate. Just check with the answer, or you can also again check the calculations. So this is the
So
step you have to do.
options are not related to point 0.7 or something. It is like 14.444 or 1.44, then 28.88 or 2.88 like.
Then I missed a 2 here. Yeah, 2 into 2 I missed here in multiplication, right? No, I have multiplied, yeah. And what is that? Half of this value will be divided by 2. Sorry, into 2 into 2. 1.4 is there in the option. 1.4. Sorry,
Yes.
0.14.
Yes, sir.
0.14. It's my e power minus 4, right? So if you want to take as microgram, then 0.014 microgram per meter cube is my answer. So I have missed somewhere 2. Just multiply with that 2. Maybe you can check with the equations again. You got it? Yeah. So that's the answer. Just recheck the calculation once. So Q is calculated by multiplying. Okay, this is the question. 1.44. Okay, I'm going again back, right? So this correct. E power minus 4 is there. So if I want to give two more, the answer is 14.44. That is correct. 14.44 may be the answer. Multiply one more 2, you will get 28 also. So 2.88 also is coming. So just check the 2. Somewhere I am missing the 2. So 14.44 is there, 2.88 also there. So just check. I'll check again the calculation. 0.05 is correct, 0.18 is correct. So if you multiply this 2, you will get this. U is 5. So sigma Z is correct, right? I will check the value for sigma Z. Sigma Z for 600 meter. So 600 meter for the stability class of overcast plate 2. D. 600 for D. What is sigma Y value? What is sigma Z? Okay, here. 600 for class D. It's around 20, 20, 21, 22 only it's coming. So it's correct. 20 is correct. So sigma Y is it 20 is approximately correct. So U is 5. So they directly given, right? 5 meter per second is your speed at okay, it's ground level speed. So no need to convert anything. 5 meter per second is correct. Root 2 pi is correct. Then I will check the formula. Which becomes 0. This will be 0. Root of 2 pi. Then there is a calculation mistake. I will calculate once. 1 second. You wait. I will take my calculator. Root of 2 into root of pi. It's 2.51 is correct into 20 into 5. 2 by answer into 0.009. 0 is 1. So H is 0. Yeah, H is 0. Yes. If it's a ground level concentration, you have to have this equation. This is correct. 2q by root of 2 pi. This is alone you have to keep. Sigma is at u root of 2 pi 2q. Okay, here is the mistake. You have to divide. No, no, no. That's already correct only. Vehicle per minute is 0.0 OD, 1.18 vehicle per meter into dispersion is 0.05 gram per second. There I multiply 0.18 into 0.05. This is also correct. Then there will be the option mistake. I will write to NPTEL team. H is 0. Yeah, H is 0 because there is no height, right? It's a vehicle. Vehicle is emitting at the ground level. So it's not above ground. How much above ground is your reset? Sorry, H. It's a effective stack height. There is no effective stack, right? Only the vehicle is emitting at the ground level. So the answer is coming as 7 only. So answer is coming as 7. 7 into 10 power minus, what is that? 0.00018 divided by 2.51 is correct. So in 10 power minus 5. So if you take 71.
Yes, sir. That's what the problem was, because after calculating also we are not getting the
Yeah.
according to
So
the
answer is
options.
actually 71 microgram per meter cube is the answer. So I'll write to NPTEL team. So just click any one option which is related, nearly related.
Okay, sir.
I will write to the team. I think if you multiply 1, 2, you will get 14. No? Into 2, you will be, yes, 143 you are getting. Yeah, 71 means 143 you are getting. So there is no option for that also. So just give the nearly correct option. I'll write to the NPTEL team regarding this. Okay. So hope you, if you have any more doubt, please ask. I'll be here in the meet. Others you can leave. Thanks. Thank you so much for joining. That's all about today. Hope you have understand about the gas in flow model around that point source, center line, and sorry, line source and the area source, and also the assimilation concepts. Thank you so much for joining. Thank you so much. Don't forget to write the assignments by the end of tomorrow. So if you are, I think the deadline for exam application is also over, right? So just go through that. So I am, and you can see my video and the PPT what I am using. Everything will be uploaded in Swayam portal. You can also go through that. Yes, go to the course. Go to the course. Exam registration is up to 28th February. If you want certificate, please apply for the examination and give the assignments properly. Exam date is 27 April. Please make it convenient to write the exam. It will be 27th April is it's Sunday. Okay. Don't forget to give the assignments. And you can see here problem solving session 2025. Here you can see my videos in the Excel sheet. You can see the Excel sheet here. So every week I am uploading the recorded videos, and also you can see in this folder all the lecture materials in the drive, Google Drive. It will be having access to everyone. So just you can download also you can use. The same material what Sar is using, I am also using. Along with that, the problem solving materials also you can see, and additionally I am posting some reading materials like AQA standard, NAQ standards. Then today I will post the Sigma Y Sigma Z graph also. Okay. Yeah. Hope this will be helpful for you. Thank you so much for joining. You can leave the meet. Thank you. Hope you have no more questions. I will end the meet. Thank you for joining. We'll meet to next Tuesday 6 to 8.